Hello, everybody. Welcome to Arqiva webinar. Today we have an exciting session. The topic for the webinar today is supply chain optimization in supply planning, how to develop a new way of thinking. The presenter is Rakesh Pillai. Rakesh is a senior supply chain consultant at Arqiva, and he has special liking for optimization, especially when it comes to the area of supply-demand balancing, or what we also call supply planning. So Rakesh, please say hello.
Hi, everyone. This is Rakesh.
Excellent. Please, let's go to the next slide. So my name is Sujit Singh, and I'll be the moderator today and helping take your questions to Rakesh. Let me start with giving you a little bit of an introduction to Arqiva. Arqiva has been in business since '93, and pretty much from the very beginning, we have focused on supply chain planning as our core area, and that's all we do. And our efforts have been recognized by many different parties. Gartner recently, in their latest Magic Quadrant publication, has put us in the visionary quadrant, which we are very excited to be on. We work with a lot of companies across the globe. As you can see from the map, we have customers, around the globe. And at this time, we have 17,000 plus users. And one of the metrics that we track is how much revenue of our customers is being planned through Arqiva, and that is in excess of $70 billion. So we are very excited about that. Now, we have built an industry agnostic solution when it comes to supply chain planning. We work with chemical, petrochemical, CPG, distributors, retail, so many different industries. And Arqiva is a global company. We started here in Wilmington, Delaware. We have offices in North America, but also in Europe as well as in Asia Pacific. Next slide, please. When it comes to what we deliver for our customers, we have a full suite S&OP solution. And really, a lot of our projects begin with demand planning. The idea being to get the best possible forward-looking demand statement. Then we typically deal with inventory, how much safety stock to carry, where to carry it. We have demand and supply synergy, or demand and supply balancing, which is the area where Rakesh will talk today. This is where we typically use optimization as well as other tools, which again Rakesh will mention. We connect that to capacity planning, and then we help support the S&OP process itself, be it monitoring, be it visualization, and be it execution. And across all these areas, we make sure to integrate financial planning so that our S&OP does not stop at S&OP. It takes the flavor of integrated business planning, or IBP. All of this is run through a centralized in-memory database, which we call Orbit. And so that's the solution we deliver to our customers. And depending on the individual customer, they might implement all of it, parts of it, only certain modules, and so on and so forth. All right, so it's time now for me to turn this over to Rakesh, who will take us through the agenda and then the material for the presentation. Now, if you have questions in the GoToMeeting panel, there is a section for questions. Please feel free to send them to us. We'll certainly try to keep some time at the end to answer your questions. With all that said, Rakesh, it's over to you.
Thanks, Sujit. Welcome, everyone, to the webinar. The slide you're seeing right now gives you an agenda for today. We will begin by looking at different types of supply planning models, their use cases, whether they use an algorithm or they are planned manually, their time frames, what they are used for, what planning levels they usually have, and so on. Then we will discuss rule-based models, what they are, how they are defined, their advantages and disadvantages, etc. in brief. From that point forward, we will discuss the use of optimization models in supply planning. different kinds of models that we could have, how they contrast with rule-based models, and their pros and cons. We will talk a bit about some of the things that are included or should be included in these models, and the practices that we should try to avoid when building and implementing these models. We will go over a little bit of validation tips, some of them that we usually use. We'll talk about what users should look at while validating results from an optimization model. Particularly, these are particularly useful if users are more accustomed to a rule-based engine or a manual planning background. Then we will conclude with some final thoughts. So in general, we build planning models for several requirements, for planning requirements like strategic, tactical, or operational. These are the level of decisions we make and also the time frames that they span. As the graphic suggests, strategic models are fairly high level, usually spanning 5 years or more. Tactical models are more medium term, 2 to 3 years is very common. Operational models are very short term, used for near-term planning. They span maybe 6 months or less. There are also models that are built to render specific functionalities like MRP, DRP, CRP, etc. But these have been separate systems maybe 15, 20 years ago. Right now, what is more common is to have one model, either any kind of algorithm in the backend. It will be one model that will detail one or more of these features, and the other features might be modeled a little bit in brief. For example, an MPS model, which is usually used to give you a production plan, could give you an MRP calculation and give you a bomb explosion and the component consumption, and so on. It could also show you plant transfers to different locations and warehouses to meet customer demand and provide you with a calculation of production hours depending on the production plan as well. So that will help you create used and unused capacity metrics and use that to figure out how much capacity is being used as well. So these are all usually features which are modeled in detail in one or more of these components, but most models nowadays integrate more than one of these features in the definition. Right. Based on the requirement of the model, when we try to model a process in supply planning and we try to get into details of one of them, usually we will require one particular feature in detail, but there is always a tendency to add more than one. But when it comes to that, based on the requirement, what we suggest is to have one feature or one or two features modeled in detail and other ones put in there just to complete the picture. If it is required to have detailed planning for more than one of these components, what we usually suggest is to have more than one model. For example, a good example is an MPS model that is usually built to plan production. We will have detailed production constraints and rules in there, similar to changeovers or modeling campaigns, lot sizes, etc. But maybe the transfers and all of those may not be modeled in such detail. Now, based on algorithms used in these models, we can classify them as broadly as manual, rule-based, or optimization. We will look at manual planning a little bit, talk about rule-based in brief, and we'll look at optimization in more detail. We all know what manual planning is, those Excel spreadsheets that we have, which we create to plan our supply, which is usually have formulas in the backend to help calculate quantities. Those are a very good example of manual planning. Rule-based models, on the other hand, are calculation engines that have a supply chain context built in, and they have a hierarchy of rules. They evaluate those rules in some order, usually by period, and calculate quantities like production, transfer, or purchase, which makes up the supply or replenishment plan. We'll go over rule-based models in a little bit more detail in coming slides. Coming to optimization models, they are actually mathematical constructs. They only understand variables, constraints, and objective function. What we do is we model supply chain decision problems using these constructs and optimize the total cost. So all the decisions or quantities that are calculated, which finally become a supply plan or a replenishment plan, are those corresponding to a lowest cost or a highest profit situation. Next, we have a poll.
All
Sujit,
right.
can you?
All right. So this brings us to the user participation, audience participation section. We have a poll. I'll go ahead and launch it. This poll asks the question, what types of models do you use for supply planning? And the options are manual, rule-based optimization, or if you're not sure, you can certainly pick that option. Rakesh did just describe for us the meaning of these terms. So let's have a few seconds for you to poll. Rakesh, what do you anticipate? Lots of people will be on the manual planning using Excel, you think?
I would expect so, because Excel is one of the most common softwares out there, and whenever we have any kind of time bound or time constrained planning requirement, that's the first software we go to.
Sure. All right, we have good activity on the poll. Let's see, it's been about 30 seconds plus. So let me go ahead and close the poll and share the results. So indeed, a majority of the people do use manual planning. Now we presage the next question a little bit. But anyway, 53% use manual planning, and the second is rule-based. Let's go to the next poll, which deals with the question, what software, if any, do you use? Now, we saw that many people use manual planning. So let's see, if Excel is the choice. The choices here are Excel, inbuilt ERP, any best of breed systems like Archiva, or custom built software. So again, I've launched the poll, and we will see, and we will give you about 30 seconds. So Rakesh, as we were talking, it did turn out that most people do use manual planning. And our best guess, I suppose your best guess is that a lot of that will fall in the Excel category.
Yeah, that's what I expect from the poll results from the previous slide.
Okay, very good. So we give it about 10 more seconds. People are voting. We see the about 40 seconds have gone by. So let's go ahead and close this poll and let's share it. It does look like Excel and inbuilt ERP are the winners. Now, some of you may be wondering how come the percentages add up to more than 100%. That's because we have allowed multiple answers, so people can select multiple answers. So anyway, Rakesh, as you thought, Excel is one of the winners, at least, if not the outright winner, but inbuilt functionality in ERP is also one of the quite commonly used systems. All right, so that with that, I will turn this back over to you.
Yeah, thanks, Sujit. Very interesting poll results. Now let's go to a discussion on rule-based models. What these models usually do is that they create a supply or replenishment plan by evaluating a hierarchy of rules. That's why we have that name. We could have multiple flavors or different flavors of these systems. An example of a hierarchy of rule is shown in the slide. When we go from left to right, the first priority of using inventory is the priority which starts with using it for meeting demand. Demand is the highest priority item usually. So when you have inventory and there is a demand in a particular location for a product at a time period, so the first thing to do is to meet that demand using that inventory. So the next priority item, so let's say you have a plant which has demand and you also require inventory to be sent out to a different location. You also need to produce something which requires this item. It's a dependent item. In that case, the second priority would most probably be the transfer requirement, which goes to a warehouse or another customer location to meet their demand. And the dependent demand that comes off from BOM calculations, MRP calculations that may be going into a product that has demand of its own. So that comes as a second priority. So the last priority in that list is to use the inventory for safety stock. That is to keep the inventory based to meet the safety stock. It is very much possible that because this is the last priority, if there is no way of not enough inventory to meet the other two, then the safety stock may not be met. So when it comes to using inventory, those are some ways of using it, some examples of hierarchies. We talked about having inventory to meet demand. Let's say you have inventory to meet all your demand or maybe a portion of it. The hierarchy usually for that is to prioritize open orders. Open orders are realized forecast or the orders that you already committed. So the usual practice or the common sense practice is to use inventory to meet open orders first, and that is what a rule-based engine also does. The next in that list is to use that for forecast. So in using demand, using inventory to meet demand, after open orders, we'll have forecast. There might be different types of forecast. All of them are evaluated in sequence. We talked about a plant with production. There could be multiple source locations, multiple plants, maybe feeding the same warehouse or a network in the chain. So when you're transferring items between these locations for meeting demand, there could be preferences, and rule-based systems will require that information to make a decision on what item has to be sent from which location. So the model will make a decision on transfers based on this location preference. There could also be cases where a particular location have multiple work centers and different production versions to create the same product, to produce the same product, and the way it chooses between those is again going by this preference and evaluating them in a sequence, right? When we come to transfers, we talked about having inventory to transfer to other locations. Again, the same example when you have multiple source locations to transfer it from. There is another constraint in there, that is the lead time. So if you have, let's say, a 2-week lead time to get your warehouse and you are already in the first week of planning, if you have a demand on the next week, it is likely that you won't be able to meet that demand, and that's because of the lead time. So the rule-based engines will evaluate lead time along with the source preference to get the item into the destination regions. Right. The final word on the rule-based systems here is that they try to meet demand. That is their ultimate purpose by following a sequence of rules. But they do not do that by using any kind of cost or penalties, which we will get to. It's a very important deciding factor for optimization models. So the distinction between a rule-based engine and optimization engine, very easily we can say it is the involvement of cost in making these decisions. So looking at advantages of rule-based models, the first thing that we usually get from users, it's usually very easy to understand the results. And that is because most of the decisions made by rule-based engines are very similar to what a manual planner, when a planner does planning by himself, would do to create supply. Right? For example, when we have production, for meeting a demand, it can easily be traced to what work center it is made, or on the other way, what demand or order is it used to satisfy. Quantity used to meet demand at a warehouse can also be traced back to a production at a preferred location, and even to a work center in that particular site. These algorithms are usually very deterministic and linear. So the advantage is when you have a particular size of problem, when you increase that problem to a number of items, maybe to give a quick example, let's say we are planning a supply chain with like 500 items or maybe 5,000 items. And let's say the model takes about 10 minutes to solve. If the supply chains changed in the future and you started getting more and more items in the system, let's say it increased to 10,000, you can be confident that the model will still solve maybe under half an hour. So the increase in solve time is mostly linear, and it can be expected that it will still solve in a reasonable time. So this is a very important advantage, because most of the higher size models, like the bigger size models, we can solve with rule-based models much faster than, let's say, using an optimization model. Right. Disadvantages, usually the rule-based models, the way they do it, the ability to do it in a linear or deterministic fashion comes from the fact that most of them make decisions on a period-to-period basis, so one period at a time. So the disadvantage there is it doesn't see the future or doesn't account for what is happening in the future before it makes a decision. A good example to give is, for example, if you have a warehouse which has a demand, let's say next week, and a rule-based engine will see the lead time, let's say it's 7 days. It'll plan for a shipment today to meet that demand. But when it goes to tomorrow, it'll see there's another demand coming up maybe 2 days after, maybe next week, maybe on Wednesday, it'll plan another transfer for that, and so on. But if something like this gets input in an optimization model, before even making the first transfer, it will actually see the demand pattern of that destination, and will most probably consolidate that and put that in a bigger truck or a lot size so that it can go together, reducing the total transfer cost. Coming from that, we could maybe look at the plan created by the rule-based engine and come up with an alternate plan, which might actually be a better plan in terms of cost, and that says that the plan that we had initially was feasible, but obviously not optimal. We will maybe able to create better plans in terms of cost very easily. So most of these rule-based engines, I said they have a supply chain context. They are usually pre-built. Like when you implement a model, you already have that pre-built, and they have that context and the industry rules set in them, and they are already set on their ways. So it's not that easy to increase or change them. Particularly if your line of work or your particular business has a specific rule or a constraint that affects only your company, then it might be really hard to put that into the mix. Right. Coming to optimization models, we will look at how they are, what they are, and also look at some of the types of models and so on, their advantages and all of that. So to define an optimization model, it is an application in supply chain, but it's actually a mathematical construct. It only has 3 things. It only understands 3 things: variables, constraints, and objective functions. Using these 3 things, we could, in theory, model any decision problem. We use that to model supply chain decision problems, and that is how we use that to create a supply plan. All outputs or decisions that we need the model to to decide on or to calculate are modeled as decision variables. Here we have an example of met demand, plan production, projected inventory, etc. Here I say met demand is a decision variable because we have input demand, which is coming from your demand management system as an input, right? That is a demand that you want the model to meet, or you want majority of that to be met, but the model makes a decision on what portion of that to meet. It bases that decision on constraints and the costs of meeting demand and all of that, but it is a decision to meet a full demand or portion of it. So that's why that met demand is a decision variable and not an input. Looking at constraints, we have one example here which says the plant production multiplied by production rate should be less than or equal to available capacity. The left-hand side of that equation, the production multiplied by rate will give you the total hours, production hours, and we say that it should be less than or equal to available capacity. So what that constraint does, it can be evaluated at a work center or location, and it will limit production to be less than the available capacity. So that is the constraint that makes the supply plan capacity feasible, right? We usually have another constraint, which I don't have in the slide, which is very common, or it's actually very important in a supply planning model, which we call material balance constraint. The material balance usually says that all incoming quantities should be equal to outgoing quantities. What I mean by incoming quantities are the ones that actually create inventory, like starting inventory at the start of the horizon. That is inventory that we have already. The production that is fixed or planned, which creates inventory. Products that are transferred to a location, which is an incoming inventory, in transits, and so on. The ones that are outgoing are ending inventory at any given time period, consumption for production, consumption for transfer to a location, and so on. So the material balance constraint will make sure that all these incomings and outgoings are matched, and hence the supply plan that it gives at the end will be material feasible. We are not actually creating materials without consuming or without incurring the cost of purchasing them or transferring them and so on. Right. So another effect of that material balance constraint is that in coming to this particular example, we cannot have a met demand which doesn't exist. Like if you are trying to meet a demand, let's say of 50 units, you can only meet that demand if there is some kind of incoming inventory to meet that demand. Like if you're producing something, producing in excess or equal to 50 units, which is equal to demand, or if you had starting inventory, or if you transferred it from somewhere and so on. So that makes sure that the demand that we meet is material feasible. All right. So the objective, the third example in there, it says that maximize met demand. Usually the objectives are either maximizing something or minimizing something else. So here we say that maximizing met demand is like we multiply that with profit and we get maximum profit. So here I am assuming the profit is 1 for every unit. So maximizing 1 multiplied by met demand is effectively maximizing met demand. We could also have a case where we will minimize unmet demand, which will on the other side increase the met demand variable. All right. So those are objective functions, and that objective drives how the optimization happens. So what the optimization models, or once we build a model, what happens next is we use a solver, which is a specialized software to solve that model. So what the solver does is it finds values of decision variables that optimize the objective function, and this maximization or minimization process will be limited by the constraints in the model. Right? Based on what we try to model, there could be different kinds of models. We have only listed 2 here, linear and mixed integer models. There could be nonlinear models, cone programs, and so on, which we are not talking about today. So we do have these 2 here because these are the most commonly used models in supply chain. Linear models, what they mean is all decision variables are continuous. So demand, if it is not lot sized, and it's possible to have 50.5 or 50.1 or something like that as a valid decision, those are all examples of continuous variables. So anything that we don't have any special consideration on what values they can take, any positive values, any fractions, they fall into the linear category. Mixed integer models, on the other hand, are used for modeling very specific or special constraints in production or transfer. A very good example is lot sizing. When we produce, we usually try to batch size our production, and to do that, we need to say that production should be an incremental multiple of your batch size. So to model that incremental multiple, we need an integer variable. Similarly, we could have minimum lot sizes where when you have to produce at least some quantity, and after that it could be anything else, or it could be a multiple of incremental lot size. To implement a minimum lot size, we need a binary, and using binaries or integer variables in a model makes a linear model mixed integer model. So as you can see from the description, most of the production or transfer related decisions in a supply planning system can be modeled using either linear or mixed integer models. Right. So one specific difference when we talk about optimization models from a rule-based engine is, in rule-based engine we talked about having a sequence of hierarchies of rules. Here we have preferences and constraints. Right. So instead of providing a rule saying that open orders are to be met first in a rule-based model, what we say in an optimization model is we have a high cost of meeting an open order or a high profit of meeting an open order. So they will have a higher cost than forecast. So naturally, they will get met first. Each of the decision variables could have a preference, and that's what we talked about when we multiply the preference weighted by the decision variable, we get the objective, and that's how we define the preferences in the model. We could also have rules which we define as constraints, as we talked about. So we looked at linear and mixed integer models. These are all, the definition or the difference in the naming is just by what kind of variables are being used, and not too much on what kind of constraints or objective is used. So when we solve these models, when you solve an optimization model, there are two cases. When we are solving a linear model, we are guaranteed to have an optimal solution. But when we solve a mixed integer model, we are guaranteed only a solution which falls within a tolerance. The tolerance is used so that the best solution that we get and the best solution possible is, the difference between them is as small as possible. And usually the tolerance is pretty low, and for all intents and purposes, they are so tight that it doesn't make much difference. But there are cases where that tolerance would affect the solution, and we will come to that in a slide, I think in a couple of minutes. All right, looking at advantages of an optimization model. So one of the first advantages that comes to mind is that they are very well suited if you have several choices, right? When we talked about rule-based models, we discussed if you have choices, you have to provide a preference on what is, what you need or what you prefer, and the model will try to evaluate that in a sequential manner. Which is true partly here, because if you have preferences, you still need to provide that for an optimization model, but the decision that it takes is not bound by the rules. It is more on the total cost. So because of that, it is able to pick solutions from a huge bunch of choices just because that particular choice is more profitable, right? One example here is that I've chosen is when you have multiple orders and you are capacity constrained, an optimization model might choose the most profitable order to meet, so that because the total that gives you the most biggest profit across the horizon, just not that order, but when you use that to improve the total cost, that is the most profitable choice. We could also see, for example, that a particular work center is selected to produce an item, assuming the item can be done in multiple work centers. It produces an item in that particular work center, which again increases the total profit, or reduces the total cost of production. One difference or an advantage of an optimization model is when it solves these constraints. When it solves an optimization model, all the constraints are solved simultaneously, which is again different from what rule-based models we talked about, it solving or figuring out the quantities in a sequential manner. Here, all the constraints are open and evaluated simultaneously before it gets to the optimal solution. And because of that, the results that we get is actually a global optimum when in the context of that objective function. Another advantage is it's easier to add custom constraints, particularly if your company has a specific constraint that you work under, and it's different from maybe a wider supply chain constraint. We could add that into the model as long as we can represent that mathematically, right? So these are also called prescriptive models. Optimization is also called prescriptive models. That is because when you create an optimization model and we solve it for a particular solution, it will give you what the best solution is, and it also gives you steps to get to that best solution. So it's kind of prescribes steps for the best outcome, right? So anything we have advantages, there will be disadvantages. Optimization models are no different. One of the biggest disadvantages that I have felt is most of these optimization models, they are not, they are general enough that they are not bound to any kind of supply chain context. So all business rules, including the simplest of them, had to be put in each time. When you're building any model, you have to put these in first. There are maybe a handful of constraints that are common across companies and industries, but again, different models have different levels of aggregation, different details that we need to put in. So we try to do that on an implementation to implementation basis. We talked about having a linear solve for rule-based models, which I said was a very good big advantage for them, but that is not the case in terms of, in the case of an optimization model. Here, if you have huge change in data, if you're adding a new location, or if you have a bunch of work centers adding a lot of items in the future, most probably you'll have to go back and see if the model is solving in time, or is it giving solutions that within the tolerance and so on. You would most probably experience a longer solve. So similarly, if you have data taken out of the model, you could expect it to solve faster, but how much faster or how much slower cannot be expected. You cannot be sure that it will solve within 2 times the size if you have increased the size twice, or any kind of approximation. And because of that, optimization models with combinations which are more or large combinations are usually slower to solve compared to a rule-based engine of a similar size. And as he's talked about how they make decisions, they look at the entire horizon, they look at all constraints simultaneously, which also translates to more computation. It has to run more calculations in the backend before it creates or it decides the value or solution of those variables, which makes it computationally intensive. You would most probably require a better CPU or a better resource to solve these models when compared to a rule-based implementation. All right. So coming into a discussion on what these models should include, mostly things that have to be part of the model based on what you're trying to implement, and also the things that you most probably should stay clear of. So what we usually say is always start with the basic constraints, irrespective of what the final model you have in mind or final construct that you have. Always start with the basic constraints of supply chain, material balance, inventory balance, and so on. One advantage of doing in this fashion is for users to look at this and understand what the model is doing, how it is doing it, and get a flavor of what an optimization model is, particularly if you have not seen one or worked with one in the past. Right? This also helps to validate data at some point, because these are all just models that working on input data. So if the data is not up to mark, then you will also have solutions that are not up to mark. So this will also help you validate data to some extent. Once you're comfortable with the basic setup, once you've validated data, once you've looked at the results of the basic model, we could always add more constraints and get to the level that you need. But usually what we see is we always keep adding more constraints to the optimization models, and at some point it will just stop having any useful information coming out of the model. So there should be a point at which you have to stop adding constraints and reevaluate what the model is doing and what it should do. And that is something that we will talk about now. We could add more and more constraints, as we talked about, but the keyword here is we should have the constraints that will reflect your business's core rules close enough. So what is close enough here is try to avoid adding all the edge cases that you will have in your business. When I say edge cases, what I really mean is those constraints or rules that you have for a very small combination or very small subset of items or locations that you plan, and try to think about and decide whether you need to have those in a planning model. And this again goes back to what the model is supposed to do. Is it a strategic model? Is it looking at 5 years or 3 years or something? And does these rules which affect a very small combination make sense in such a horizon? Right. You should also have a clear order of preferences, and this is a requirement or an issue with the optimization models. When you have costs, which we talked about, is driving the optimization as part of the objective function. When you have similar cost for different decision variables, it gets a little bit tricky with the solving software. It finds it tricky to figure out which direction to go, and it kind of gets stuck in a loop. So to avoid that, one thing we recommend is to use actual costs of the system in the business. The advantage there is usually these costs are all calculated based on the effort required to produce or purchase something, and they are representative of the value of the product that we get. So that's a very good way to cost the model. But to be clear, optimization is actually a representative model, so you don't actually have to have actual costs. We could have, for example, a directional cost and get similar value. An example is if you have a product that is twice as expensive as another product, you could have $1 for one product and $2 for the other. It will give you the similar results. But then again, if you want to look at the results from a financial perspective, you have to convert these numbers again back to your terms by multiplying them with the actual costs. All right. what I talked about, not adding every edge case. You also talked about what I meant by edge case. So another side thing to talk about there is when you add more of these constraints, invariably the model becomes big and complicated and becomes hard to solve. But if that is the core requirement, if you're adding a constraint that is a core business requirement and the model is hard to solve, we'll have to figure out how to solve it, better optimize solve time. But if that doesn't give you the value that you require, usually that effort required to make it optimize the solve time is usually not worth the effort, right? So when we discussed the differences between the optimization and rule-based models, we talked about having preferences and limitations. I said preferences are usually the cost that we apply to the objective function. We say that some of these activities are more preferable than the other. All of those goes in as either cost or a preference number for the objective. Limitations are the hard constraints, the things that you cannot violate in a supply chain system. A very good example is something that I came across sometime in the past. We had like a production plan where you have inventory on tanks, where there was like 5 million pound of inventory that can be put in tanks, but the user who was planning it, he was using manual planning, and it's not very easy to see the inventory change across different products. So what they had was a limit on 3 million pounds, right? And that was not just because of the storage limit, it was also because they didn't want the production to change drastically between days. So they didn't want the production to be, let's say 4 million pounds on one day and maybe 1 million pounds on the next day. They want to have it maybe 3 or 2.5 million pounds as we go in a week. So the first one, the limit 5 million pound, is a limitation. It's a hard constraint that the model should not violate. But the second one, the 3 million pounds, is actually more of a preference. They want the production to be load leveled, but it is not a limiting factor. It is not required that the model cannot make more than 3 or 3.5 million pounds. If it is required, if there is demand to meet it, it can very well do it. And that is the deciding factor on what is a preference and what is a limitation. And when you're building an optimization model, this has to be very clear, right? So the rule on that, or the final reading on that, is if you have something that is more of a preference than limitation, don't add that as a limitation. A model with more preferences and less limitations are easier to solve than the ones with more limitations or constraints. Usually when we build models, it is not uncommon to see users using the same model for all the applications. Tactical models are usually the first thing that gets built, and we have seen cases where people run that for strategic uses, which is for a 5-year horizon. It is not it is not frowned upon, or it is not bad. If you can run it in your resource, it's fine and good. The disadvantage of doing that is that it creates a supply plan which is more detailed than what you need, and for a horizon that is it's too long. So the entire plan would be too detailed. It usually creates more problems than it solves, and it also usually takes a long time to solve. So a better response time, if that is what you're looking for, then you should look at maybe building another model just for that application, right? In that case, if you are building one, if you create a strategic plan, that will give you better response time as well. So if you need to, if you are in that time of the year where you are figuring out strategic outlook, or if you're trying to figure out a strategic supply plan, the better response time will help you, get results faster. An example there is, we had instances where we have an MPS model which is supposed to plan production in a plant system. We have multiple plants sending products to warehouses. Production in plants, it's part of the MPS model. It's modeled in detail, but the transfer to the warehouses are planned because you need to have some form of DRP features in there. But what happens when it finally gets to the warehouse? Do you need to look at how that inventory is getting used for meeting customer demand? Most probably you don't, because that inventory is already part of the decisions made by the MPS model. And how you distribute that? Do you do lot sizing there, or do you plan your truckloads with palletization and all of that? It is not very important to for the MPS model to know that, because it doesn't affect decisions made by the MPS model. Right? Another distinction that could help people make better models is to avoid putting execution decisions in a planning model. A very good example is FIFO, which is first in first out. It is a way of using inventory for meeting demand or transfers. We all know when we have production, it is done in lots and sometimes with specific lot number, and it is very nice to see these batches go and meet demand. And if you're able to trace it, it's very useful for some part of the supply chain. But however, this is usually not a responsibility of a planning model. A planning model does not need to keep track of batches to make decisions. That said, there are cases where that is not true. An example is a dairy product manufacturer where you cannot sell products which are older than a particular number of weeks or days old, in which case you have to track age, which translates to tracking the batch where it is produced. Another example is pharmaceuticals, where traceability is a very important legal parameter, where you need to be able to track which work center has produced a particular batch of products and so on. Right. Another thing to keep in mind while adding stuff to optimization model is to think about whether that particular constraint or a decision variable is actually taking part in the optimization, or is it merely a calculation. Right. One of the examples that we have seen in the past is to have the supply planning model reduced unused hours. This is a very common requirement because usually the supply planners would like to have their work centers utilized maximum. But at this point, the problem is if you ask the optimization model to reduce unused hours, in that I say if you load the objective functions to say there's a cost of not using capacity, what will most probably happen is that it will select a product that is produced the slowest, which has the lowest production rate, and use that to fill the capacity. So what happens with that is when you have that product coming out of the production, it consumes the most capacity of all the other products. It will also not add to the inventory holding cost that much, right? Because it is very, very slow to produce. So that may not be the result that you're looking for, and it might actually puzzle you on why that was selected to produce. The answer is because it actually reduced the total cost. But in this case, that answer is not usually acceptable. So what we suggest at this time is there is no solution for that in an optimization model. We cannot optimize the model to pick something else which goes against the total cost objective. So what we usually suggest is to look at that decision and see if we can use that capacity, maybe take that to the sales department and ask them what kind of products do they need to be given so that they can sell it, right? And if you are doing the planning for a while, you would most probably know for the company and the market you are in, you would most probably know what products sells faster, and you could just put that as the preferred product. And in that case, we will not have that as part of the optimization, but we will run the optimization model, get the unused capacity, then schedule this product to be produced on the work center that has available capacity. So the output will look similar to what the output would be from an optimization model, but that particular decision, which is actually a calculation and not a an optimization decision, it is much easier to implement, and also much better decision. Right. Validations, when you look at the result of an optimization model, it is very common that you will get a result that you do not understand fully. A product that you always thought is high priority due to demand might be produced less because there are other products that could have better total profit, or a product that may be produced in a different work center than what you usually produce. That is because maybe by clearing that work center of that product, other products can be made on that work center that increases the overall result, right? So again, total cost is the driver. That is what makes the optimization model make its decisions. So when you look at something like this, try to look at what the actual numbers are doing, and trace it back so that you will make sense of what is happening in the plan. Verifying the result. When you verify a result, what we suggest is looking at your KPIs that you usually use for benchmarking your supply plan, and not look at the minor decisions that the model is making to getting there, right? If you see something that is done, as I mentioned earlier, if the product is being made in a different work center, may not be what you expected, but it still improves your total cost. It may not be the way that you have done it in the past, but if it is better, you should be willing to look at it in a different perspective. That said, we could have issues where, as I talked about in a previous slide, we have this thing called tolerance when you look at integer models. There are cases that I've seen where the decision falls in that tolerance gap and the model doesn't actually optimize it. And this is very rare. It happens sometimes when you have products that have, let's say, 1 million units of demand, and also products that are nearing their end of life and have unit numbers of demand like less than 10. So whatever you do with that last 10 units of demand, it is not going to increase or decrease your profit too much, because you get a huge amount of huge number as the profit by meeting the demand of that 1 million unit product. So the decisions that the model make for that smaller demand product is too small to make a change in the total cost. So in that case, this could happen. So in this is not something that you will have to work with in the result. It's something that we need to look at at the modeling phase and see if there are decisions like that. And there are ways to fix that by either partitioning the model or rescaling the costs and so on. And another thing that we usually tell our clients is to look at those products and see if they are actually required to be planned. If it is actually end of life products, they will have some kind of a stable tailing demand, which can be done, which can be planned even without an optimization model. Right. So coming to the conclusion, we talked about different algorithms, and we talked about how they serve different purposes. So one of the output of that is the decisions given by, or the results given by these models will also be fundamentally different. When you evaluate those results, think about what kind of features you need in the model, what kind of models or what features in the model are you actually looking for, and use the benchmark that you normally use to to evaluate the supply plan to evaluate the results of this model as well. If you see a result which is better in total cost, and if you cannot find a way to reject those results, you should be willing to accept that it is possibly a better result. And finally, models are all here for decision support. It is for you to get a baseline on your plan. It is always your plan to make, so you can override the numbers given by the model and make your own plan. So that is what I meant by these are not meant for decision making. So based on how your planning team responds to the results from these optimization models, and how you respond to the counterintuitive results some of the time, that will dictate how your optimization model implementation and the project will finally turn out. With that, I conclude my presentation, and we are open for questions.
Rakesh, could you go to the next slide, please?
Oh, sorry.
Right. So this was, thank you, Rakesh. That was very insightful. I hope we will get some questions here. Of course, if anyone is interested in getting a demo of optimization in the supply chain space, we are here for them. So Rakesh, one of the things I picked up on was your distinction between the rule-based versus the optimization. And by the way, folks, if you want to send us questions, please do through the GoToMeeting panel, the questions tab on it. So Rakesh, for the rule-based, it seems since you are identifying the way you work and apply them into rules, it might come to an answer faster, but it will be very close to how you would have done it manually. Therefore, like you said, more understandable and so on. The new way of thinking, as our title of today suggests, comes from optimization, in that it's creating counterintuitive results that you would have never considered in the past. And just in that way, opens your brain up to possibilities that you maybe did not even know that existed. And so that was my learning, that really, because of the counterintuitive output, that makes it that much more powerful, which a rule-based or a manual system will have a very rough time getting to.
Absolutely. Actually, the advantage of having an optimization model is it'll look at all possibilities and evaluate all possibilities and give you a result that maximizes the objective. That is something that is absent in a rule-based model, right? It doesn't look at all the possibilities. If it finds a solution with the first preference, it will just take that and give you as a solution. So in that case, it is always better to use an optimization model when you have multiple or several choices.
Right. I suppose one question that has come in is it possible to set up optimization in Excel-based models? I suppose easier models are easy to set up, but if you want something very complex, you should move to a more advanced system. What would you say?
Yeah, sure. Because Excel has a way of setting up models and using a solver to solve them. But as you said, when you start adding more items or when you're trying to put more locations to optimize, it becomes a limiting factor very soon.
Right. One of the other questions that have come in is the optimization model seems to intimidate the leadership and appear to be a bit of a black box in terms of how they solve. How have you worked with clients to shift this misconception over time? The proof is in the pudding of results and in the total ability to solve and resolve quickly. So really the question is around, results come out, the management team is not very trusting of it, think of it as a black box. How do you convince people that these are good results?
Yeah, usually that is the first step in getting acceptance for these models. So what we usually do is to do kind of an iterative implementation. When we have optimization models, we start with the most basic models and give them the results to look at, which at that time we'll get all these questions on what is being done, why is doing something that we didn't expect before, and so on. So we try to address them at that point before we get into more complicated business rules and implementations of that. So by the time we get there and people have already looked at the result at a familiar environment, they are more accepting of the fact that the model is making a decision from a best cost perspective.
Mm-hmm. Okay, so that's good. And I think Danny, in this case, the questioner, has also given this sense of, hey, proof is in the pudding of the results, but also the fast cycle of solve and resolve, which seems to imply that if there's an error, tweak something, resolve it, and hopefully within a couple of cycles get to something that management likes. It's very interesting.
Sure. Yep.
All right. Doesn't look like we have any more questions coming in. So at this point, we can try to conclude the webinar. So again, Rakesh, thank you very much for the presentation. Very insightful. And to all the attendees, thank you for attending. Thank you very much for your time and have a nice day. See you.
Thank you.